All right, grade 3 students. This is a remake of the last video that was supposed to go out Friday. Unfortunate, I'm gonna have to spend an extra, half hour going back through it, but it's okay. It'll hopefully be better this time. That's usually how things go when you do them more than one time. But we're talking about compound interest today. My Delta Math modules should be fully up to date for you. And we only have one more lesson after this that we'll get to, and then we'll be ready to test very soon. So let's go ahead and get started. All right, so to start things off today, we are going to read this quote here. So I want you, I'm gonna remove my video, and I'm gonna pause the video. I want you to read this slide. Okay, so now that you've read the slide, this is what we're talking about today. We're talking about compound interest, and it's such a big deal in human history. And it's one of the reasons I love teaching it so much is because, this is one of those lessons. You have a lot of math lessons. You're like, when am I ever going to use this? Well, here's one that every person that lives in America and really the world needs to know about this idea, okay? And when we're talking about compound interest, Albert Einstein, revered as one of the most intelligent individuals in human history, called compound interest the greatest invention in mankind, right? He called it the eighth wonder of the world. But I think the most important thing for you all today as we're going through this topic is to heed the warning down here at the bottom, because this is really the reason why I feel that I enjoy teaching this idea, is because if you can understand it, you're going to earn it. As I said, he who understands compound interest earns it. He who doesn't pays it. And what this means is if you're not educated in the ways of finance and this idea of compound interest, we're going to be diving into the mathematical sort of pure math aspect of it and get into some abstract things, then you're going to sort of fall prey to it. So that's what we say here. An uneducated population is one that's going to be paying debts. Essentially, this is talking about if you are okay with having debt and having debt most of your life, then you're going to end up paying. And this is going to be very important for a lot of you who are juniors, and I mean really all of you, but specifically the juniors in here, that compound interest is something that you take into account when you're thinking about where you want to go to college, how much student loan debt you want to have. For me, I always recommend community college. That's what I did before, and that was before I even knew I wanted to teach math. I went to community college and majored as history major, and I was going to teach history, but I took a math class. I was like, wow, this is the best thing ever. So, and I had a great teacher that sort of inspired me. So, you never know what your journey will end up going towards. So it's best to, take as little debt as possible while you're on this journey trying to figure out what you want to do with your life. So you don't want to just go to some big state school or go out of state and rack up all this debt. There's people who owe, hundreds of thousands of dollars in debt. And it's just because they aren't educated. They don't understand this idea of compound interest. They don't understand the pitfalls of just taking on so much debt. It really buries you, if you're not careful, right? So we have to be very cautious when we're going into situations with debt. Okay, so we are going to start by we're going to start with the idea, the formula of compound interest. So I'm going to go ahead and go to the next slide here. I'll move this here in the center. All right, so I need you to write down, I'm going to get out of this screen here. Oops. And we're going to write down this formula for compound interest. So start at the top. And by the way, you'll be allowed to use this formula on the test. But it's A equals P times 1 plus R over N times n to the t. So we're going to write out all the parts of this formula, okay? So write the formula first, then we're going to list out all these letters. So first off, we have principal is what that's called. You may have heard that term before. I didn't really fully understand what it meant until I was an adult, so that's fine if you don't get it now. What you need to understand it as right now is your initial amount. And we've seen that so much through all these exponentials, right? We have this initial value. We're used to seeing that as A. This is also known as the first term, okay? First term. So that is our first expression there. Part of this is principal. Okay, that's just like if I take a loan on my house, whatever the house is worth when I buy it is the principal amount. Okay. Next, we have the R. Now, this has been in our other formulas. So if we go back to growth and decay formulas here, I think we've done an example with those. This is rate of growth, rate of decay. But you'll notice with the compound interest formulas, this is always a plus sign here. And that means it's always growth, but we just call it interest rate. And whenever you go and take a loan on something, you get an interest rate. Now, this is called compound interest, so we'll talk about what a compounding is. We're going to watch a video here in a second, but this would be the number of compoundings per t. And I say t because I'm referring to this, which is time, right? And I guess I'll spell it like that. So time, and we're going to put next to time usually in years. So typically when we're doing these compoundings, and in real life especially, it's always done on a yearly basis. And you're making monthly payments. That's a typical situation, is that you make monthly payments. But we're going to be going into other intervals of time as well for this. Lastly, we have A, which is your amount at a particular time t. So if I wanted to know have I paid after 10 years of payments for a house, or if I buy a car, usually those go 3 or 5 year loans. How much will I actually pay for that car after 5 years? So we're going to be doing some examples with that as well, probably next lesson. But let's go ahead and look at an example of how we would use this. It's actually a pretty simple process. Of of just plugging parts into the formula. So I'm going to go ahead and make this large here. And we're going to read this example there. It says, Anisha invested $8,000 in an account that earns 10% interest. How much money will she have in 15 years if the interest is compounded quarterly? So I'm going to go ahead and draw on this. And right here, we see this 8,000. That is going to be our P, principal, okay? This right here, 10%, is going to be R, interest rate, which we need to write as a decimal, 0.1. Okay. And then here, this is 15 years is going to be T. And then it says compounded quarterly. So this is per year. How many times per year? We're not interested in the total number of compoundings. It's just how many per year. Well, that will be N equals 4. So now we're going to write up our function. So I'm going to actually change the way I write A up here. I want to put it as A of t. So A of t is equal to, we want 8,000 parentheses 1 plus, we have R, which is 0.1, over our number of compoundings, which is 4. And then 4 times, I'm going to keep it as t for now, okay? So this, I know it looks so sloppy when I write with a mouse, but I know you're writing it better on your paper notes, so this should all be in your notes. This is how you would construct your compound interest formula. So we want to know, after 15 years, obviously, depending on her age, I mean, she could keep this growing and growing and growing, right? She could just keep it going. But we're going to see how much is it worth in 15 years. That's what we want to know. And let me pull up my Inspire. All right, so I got my Inspire ready to go. And when I had to pull it up, it kind of got rid of all my writing, so I rewrote all this. So we're interested in finding A of 15. So this is how I would want to write this. This means I'm taking the function that I created and I'm plugging in 15 for t, so that'll go up here. So let's get up the Inspire here. I'm going to do 8,000 times 1 plus. By the way, I figured out a way, or somebody showed me a way. If you're using an 80 series, actually, I kind of want to pull that up. I'm going to show it here in a second. I'll show how you could type. You can actually type fractions in the 80 series. A student showed me that face to face, and it kind of blew my mind. So I think that's going to be a pretty big change for a lot of you guys that are distance learners on how you can type some fractions in a little bit faster. Anyway, I'm putting. Oh, my camera's in the way. Hold on, move it down. Okay, so I have it typed in. I'm going to be putting a 15 right there. That's the time in years. I hit enter, and there we get 35,198.3. This is in dollars, so we're gonna make it. We're gonna make sure that it is to 2 decimal places. So 35198.3, and I'm gonna make sure it's $35198 and 30 cents. So here is our answer to this question, and that's how you would want to answer that. That's what you'd want to do when you're working these questions. So on Delta Math, you have several questions like this. I don't feel like it's too complicated, especially if you have the formula. You're just looking for the pieces that you need. But this is really what we're focused on doing for this section. Now, we're going to move on to the next slide. Oh, actually, hold on. I want to show this for the 80 series, what you guys can do. So check this out. Those that are on the TI 80. So if you have your calculator with you, somebody showed me this. If you press alpha and then you press y equals up here, so check that out. I'll hit alpha, the green button, and then go up, hit y equals. Look what it gives you. It gives you this option number 1 here to make a fraction. Now you can type this out exactly like you would, like I did on my my 80 series here, or my Inspire. So I'm going to do 1 plus, and I can go over and do 0.1 over 4, and then raise that to the 4 times 15. There we go. So that might be a very helpful tool for you guys looking forward to ACT and things like that. Making these fractions, it's going to be a lot easier because at this point you've had to use a lot of parentheses. Now, if you're using a TI 83, I'm so sorry, this is not an option for you. You're going to have to remember the parenthesis rules. But at least this is some relief for the 80 series, or 84s, TI 84s, all of those different versions of that. And remember, that's alpha y equals, and you can click all of this. I don't know what all the others fraction to decimal there, but I'm not really sure what all of this is. You can play around with it, but I know that 1 right here is going to be the one that gives you a fraction, so that's cool. Okay, moving on. Let's look at some different aspects. So one of the this different types of compoundings. So one of the things that we see here is that our problem was compounded quarterly. So there's all different ways to be compounded, okay? And we're going to write this out. We're going to say what types of compounding, like how many compoundings would be happening if we're compounding it yearly. So that would be once, right? That's what that means. If we say semi-annually, that means 2 times, right? Quarterly, we just did that. That would be 4 times. Monthly, which is really what happens in the real world, right? We say 12 times. After that point, you're not really going to be compounding interest that much. A computer could do it, but that's not typically what is occurring. But because we're in a math class, we're going to really sort of push this to its limit and try to discover like what is the most compounding that we could do. So what would happen weekly, right? What is weekly compounding? Well, there's 52 weeks in a year, right? Bi-weekly. So this means every 2 weeks. Some of you have jobs and you get paid bi-weekly. So that means really it's not every week, we're getting it every 2 weeks. So I kind of need to divide 52 by 2, right? Bi-weekly would be 26 times a year. Okay, now we're getting a little bit crazy. Daily, there's 365 days in a year. And then we're saying hourly. 365 times, we have 60 hours. Oh, whoa, what am I doing? 24 hours a day. That is, oh, and I forgot my n equals. That is how many hours in a year? 8,760. Now we go to every minute. Again, this is us getting sort of abstract here. You're not going to be seeing this in real life. I know, as I said earlier, when am I ever going to use this? This is the thing that you're going to use. Again, there are aspects of this that we're really delving into. You would not really see this in a personal finance class, but again, we're discovering the math here. Every minute, so every hour has 60 minutes, so we're going to multiply that by 60. So 5, I'm going to copy that. I don't feel like typing it. Okay. Every second, so we need to copy, or no, we need to multiply this by 60 as well. All right, 31,536,000 seconds in a year. So there we go. We can't really divide time any further than that, or can we? We could do every half second, every tenth of a second, every thousandth of a second. Or, as this last one is saying, continuously, right? What the heck does that mean? What are we talking about when we say continuously? Well, even at the most microscopic level, because time, we could divide it into the smallest unit of measure possible and then go even smaller. Divide it by the largest number we could ever think. So what does that even look like if we're saying what value of n would go down there? What almost makes us think that we're dividing it, or that we're putting infinity here. That's what it sort of seems like. So yeah, we're really digging into something that I would consider pretty abstract, okay? So we're going to watch a video here explaining a new number that we're going to be talking about, and we're going to have to use to answer questions that say compounding continuously. Okay, we're not going to watch all of this video, but this YouTube channel is called Numberphile. You can see this video has almost 3.3 million views. This is a really good video, and I hope it helps you guys understand what compound interest is, because I haven't really even explained what it is. So I'm going to watch it. I might pause it a few times just to make some comments, but I'm going to go ahead and get it started.
So we're going to go back to the 17th century, and this is Jacob Bernoulli, and he was interested in compound interest, so earning interest on your money. So imagine you've got £1 in the bank, and you have a very generous bank, and they're going to offer you 100% interest every year. Wow, thanks a lot, bank. So 100% interest, so it means after 1 year, you'll have £2. So you've earned £1 interest, and you've got your original pound. So you now have £2. What if I offered you instead 50% interest every 6 months? Now, is that better or worse? Well, let's think about it. Okay, you're starting with £1, and then I'm going to offer you 50% interest every 6 months. So after 6 months, you now have £1.50. And then you wait another 6 months, and you're earning 50% interest on your total, which is another 75p. And then you add that on to what you had, so it's £2.25. Better.
So that's what compound interest is. So I want to pause it real quick. When we say we're compounding, it means you're taking the interest, you're doing repeated interest over the same interval of time. The top one is a year, and these are British pounds. I know that we use dollars here in America. You can just imagine these are dollars. $1 becomes $2. That's in 1 year at 100% interest. But then he takes it and he breaks that interest into 2 compounding. So you're getting 50%, but it happens twice. So what happens there? Well, you add half of what the original amount was here, and then you do it again, and you end up making 25 cents more, right? So that's kind of the power of compound interest. It's not this simple interest where I'm just doing it every year. You're having multiple, we call them compoundings. So that's what makes this so strong, is that 25 cents adds up. It may not seem like it, but over a long period of time, it's growing and growing and growing, and it can really turn into some large amounts. So that's why it's one of the most powerful ideas, right? So let's continue.
It's better. So what happens if I do this more regularly? What if I do it every month? I offer you 1/12 interest every month. Is that better? So let's think about that. So after the first month, it's going to be multiplied by this. 1 plus 1/12. So 1/12, that's your interest, and then you're adding that onto the original pound that you've got. So you do that, that's your first month. And then for your second month, you take that and multiply it again. by the same value. And in your third month, you would multiply it again and again. You actually do that 12 times in a year. So in a year, you would raise that to the power 12, and you would get £2.61. So it's actually better. In fact, the more frequent your interest is, the better the result. Let's start with every week. Okay, so if we do it for every week, how much better is that? Okay, what I'm saying is you're earning 1 over 52 interest every week. And then after the end of the year, you've got 52 weeks, and you would have £2.69. So it's getting...
You'll notice the resemblance between this and the compound interest formula we just wrote. Sorry, I just wanted to comment on that. It looks a lot like what we did for our formula.
Better and better and better. In general, you might be able to see a pattern happening here. In general, it would look like this. You'd be multiplying by 1 plus 1 over n to the power n. Hopefully you can see that pattern happening. So here n is equal to...
And that's
12,
in 1 year.
You do it every month. 52 if you do it every week. If you did it every day, it'd be £1 multiplied by 1 over 365 to the power 365. And that's equal to £2.71. And so it would get better if you did it every second or every nanosecond. What if I could do it continuously? Every instant I'm earning interest, continuous interest. What does that look like? That means if I take this formula here, 1 plus 1 over n to the n, I'm going to n 10 to infinity. That would be continuous interest. Now, what is that? What is that value? And that's what Bernoulli wanted to know. He didn't work it out. He knew it was between 2 and 3. So 50 years later, Euler worked it out. Euler, he works everything out.
Him or Gauss?
Yeah, it's either Euler or Gauss. Say Euler or Gauss, you're probably going to be right. And the value was 2.71828282845 and so on.
We were pretty close when we were doing it daily, weren't we? It was already 271 at daily.
You're right. We're getting closer, weren't we? We're getting closer and closer to this value. So already we're quite close to it. If you did it forever, though, of course, you would have this irrational number. Now, Euler called this E. He didn't name it after himself, although it is now known as the Euler constant.
Why do you call it E then?
It was just a letter. Yeah, he might have used A, B, C, and D already for something else, right? So you use the next one.
Bit of a coincidence.
It's a lovely coincidence. I fully believe that he's not being a jerk here, naming it after himself, but it's a lovely coincidence that it's E for Euler's number.
Would you have called it G if you discovered it?
I would not have called it G. No, I would have hoped somebody else would have called it G, and then I would have accepted that. Euler proved that this was irrational. He found a formula for E, which was a new formula, not this one here, a different formula, and it showed that it was irrational. I'll quickly show you that. He found that E was equal to 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 1 plus 1 over 4 plus 1 over 1 plus 1 over 1 plus 1 over 6 plus, and this goes on forever. This is a fraction that goes on forever, continuous
Pretty cool.
fraction, but you can see it goes on forever because there's a pattern, and that pattern does hold. You've got 2, 1, 1, 4, 1, 1, 6, 1, 1, 8. So you can see that pattern goes on forever, and if the fraction goes on forever, it means it's an irrational number. If it didn't go on forever, it would terminate, and if it terminates, you can write it as a fraction. And he also worked out the value for E. He did it up to 18 decimal places.
No calculator.
He had a different formula to do that. I'll show you that one. So this time, he worked out that E was equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and this is something that's going on forever. It's a nice formula. If you're happy with factorials means you're multiplying all the numbers up to that value. So if it was 4 factorial, it'd be 4 times 3 times 2 times 4.
It's a factorial.
Okay, why is E a big deal?
All right, we're gonna stop it there because he'll talk more about what that is. If you want to look up this YouTube video, watch the whole thing, you can. It's pretty cool for those that love the idea of these numbers. So let's talk about this on our calculators. Excuse me. Let's talk about E really quick because we've discovered now what what we need. We needed this new value, this Euler's number is what it's called, okay? And here is our new formula. So in your notes, draw a line, and then we have what's called, you're gonna write continually compounding interest, and you have this formula here, it's called PERT. That's how we'll describe it, PERT. And so it's A equals P times E to the RT. So R is still your interest rate. E is Euler's number, which he has already described as, he gave you the number, it's an irrational number, and then P is, of course, principal. P is your principal. So we have that. Let's talk about on the calculators where you find all of this. First off, for the 80 series, you'll see E is the blue number, it's the blue value. If you hit division, you have to hit second divide to get E. If you hit enter on that, it will give you, there's that number he described in the video. You can also hit second LN here, and it gives you an exponent. If you put 1 in there, it gives you the number. Inspire over here. If you here's the E to the X right here. If you hit, just tap that number to the first power, there it is, 2.1782. Or you can hit the little pi button down here, and there's E right there, and you hit enter. Okay, so that's the where you're going to find those. So let's talk about questions that you'll be doing. Let's look at delta math really quick. Let me adjust this just a second. All right, so I paused my recording somewhere. I'm not really sure where that happened, but I think that I got my video in there and we did all of this. Sorry. Let's look at delta math just because I'm not really sure. I'm already, let's see, we're 27 minutes in. Let's work a compound interest problem. I'm hoping that my video made it in. I think it did. So here is the sections on your delta math. What we can do now is look at this compounding problems here. So here you'll see the ones that are compounded quarterly, but we're looking for one that's continuous. So let's do this one here, okay? So using our formulas here for compound interest, that's A equals P E to the R T. We're going to answer this question. So first thing I want to do is I want to make the formula. So it says Penelope invests $32,000 in an account, paying an interest rate of 7% compounded continuously. So as soon as you see the word continuous, you know you need this formula. Assuming no deposits or withdrawals are made, how much money to the nearest dollar would be in the account after 14 years? So we're going to put 32,000 E to this rate here, R, is going to be 0.07. I'm going to put my little function notation on here as well, A of t. I'm going to go ahead and put t here. And then what I want to find is A of 14. What does that equal to? That's what's going to go in here. So I'll use the 80 series for this. Clear that. So on the 80 series, just to type this in, I'm going to do 32,000. I'm going to press second LN to get E, and I'm going to raise it to the, I need to move this over a little bit. I'm going to raise it to the 0.07 times, okay, hit the multiplication symbol, 14. So that gets me $85,262, and we'll round this up to 60. Actually, it wants the nearest dollar, the whole dollar here. That's what it says, nearest dollar. So we're going to do, this is 85263 is what we want. So 85263. Submit. And we've got it. Okay. So that's really what you're going to be doing on these problems. So at this point, I can go ahead and stop this lesson. I've shown you what I needed to. The last lesson that you'll be getting will be over graphing, and then we're planning on taking our test the 11th here. Okay, so you'll have one more lesson this week. All right,